Today we're going to introduce an object of fundamental importance, and that is the unit circle. I'm also going to redefine some of the trigonometric functions, sine, cosine, and tangent, that you've seen in previous classes. So this is a really important subject. So let's just begin by recalling the meaning of sine, cosine, and tangent. The setup is the following. Suppose you have a right triangle, so here's a right angle. Let's suppose that this angle right here is theta. Let's suppose that the side here is little a, and this side is little b, and this side is c. That would be the hypotenuse. Then the sine of theta is defined to be what? So basically the trig functions, if you remember, they are functions which accept an angle as an input. As you can see, I'm inputting the angle theta into my sine function. They accept an angle as an input, and they produce a ratio of sides as an output. The sine of theta, which ratio of sides is it? If you recall, it's the opposite side over the hypotenuse. So when I say opposite side, I mean the side opposite to theta. That would be A, over the length of the hypotenuse, which would be C. So whatever A and C are, and whatever angle theta is, the sine of theta is defined to be the length of the opposite side over the hypotenuse. And the other trig functions have similar definitions. If you recall, cosine, it's the adjacent over hypotenuse. When I say adjacent, of course, the word adjacent means next to. So the side which is next to theta is going to be B. You might say to yourself, well, I see two sides which are next to theta, which are adjacent to theta. But when we refer to the adjacent side, we're really saying the side which is next to theta but isn't the hypotenuse, and that would be B. Okay, over the length of the hypotenuse, which would be C. And then finally, we have one more trig function, and that's the tangent function. And tangent of theta, the ratio of sides is defined to be the opposite side over the adjacent side, which in this case would be the opposite side of theta would be A, and the adjacent side would be B. Okay, so that's a brief review of the three standard trigonometric functions. You've seen these in previous classes. Now, what I'm going to do today is redefine these trig functions in a different way that doesn't use triangles and instead uses something called the unit circle. So first of all, I want to start with a motivating question. So here's a question. What is the sine of 270 degrees? All right, now, why do I bring this up? First of all, if you ask your calculator what this is, if you type in sine of 270 degrees, it will give you the answer -1. Now that is really strange for all kinds of reasons. Okay, first of all, 270 degrees is not an angle that can fit inside of a right triangle, is it? I mean, in a triangle, the angles add up to 180, and 270 is already bigger than 180, so 270 degrees can't even fit inside of a triangle, and yet apparently your calculator can compute sine of 270. Well, that's strange. The other strange thing about it is that up till now, the definition that you have seen of the sine function has been a ratio of sides, opposite over hypotenuse. Well, how is it possible that a ratio of sides opposite over hypotenuse could produce a negative number? I mean, these two side lengths are distances. They have to be positive, and yet apparently their ratio is -1. Something really strange is happening here. And what's happening basically is that your calculator is not using this definition of the sine function. It's using a new definition using the unit circle, which I'm going to explain. And as we'll see, this new definition allows us to compute the values of the trig functions for new angles. We couldn't use this definition to compute sine of 270, but the definition I'm about to give you will allow you to compute sine of 270. So we sort of expand the range of angles that we can actually analyze through trig functions. Okay, so how do we define the trig function? So this is the new definition. New definitions of sine, cosine, and tangent. So how does it work? So here's the idea. Let theta be some angle. Okay, I don't care what it is, whether it's 45 degrees or 60 degrees, whatever it is, it's just some angle. And this is the angle that we would like to evaluate at the trig functions. We would like to compute, in other words, sine of theta, cosine of theta, and tangent of theta. How do you do it? Here's what you do. You begin by putting your angle theta in standard position. Remember we talked about this? So what does that mean, to put an angle in standard position? It means you put one side of the angle along the positive x-axis, like this, and then you open the other side of the angle appropriately until you've reached the desired angle. Remember, if theta is positive, then you open it counterclockwise, and if theta is negative, then you open it counterclockwise. So let's suppose that my angle is something like this. Maybe it's like 50 degrees or something like that. So there's my angle theta. Now what do? What we do is we draw a circle centered at the origin of radius r. So I'm going to construct a circle centered at the origin, and this circle has radius r, let's suppose. All right? Now you'll notice that the terminal side of my angle, that's this side right here, intersects the circle at some point. Okay? I don't know what that point is. Surely it depends upon the radius r of the circle, and of course it also depends upon the angle theta. But whatever this point is, I'm going to call the coordinates of this point x and y. So x is just whatever the x-coordinate of this intersection point is, and y is just whatever the y-coordinate of this intersection point is. And now I'm ready to define my trig functions. So we define the sine of theta to be equal to y divided by r. That's the y-coordinate of this intersection point divided by r, which is the radius of the circle that I drew. We're going to define the cosine of theta to be equal to x over r. And we're going to define the tangent of theta to be equal to y over x. So these are new definitions. I have two things to show you. I want to eventually convince you that this definition, even though it seems so different from the old right triangle trig definition, actually coincides and agrees with the old definition. I'll show that to you in a moment. But there's kind of a more pressing issue. These definitions that I have written down seem to depend upon r. I mean, obviously, the radius r of the circle that you draw is kind of up to you, and yet we've got an r appearing in the definition. Well, in order for these functions to be well defined, it had better not matter what radius you choose. Okay, I claim it actually doesn't matter the radius of the circle. Believe it or not, it doesn't matter what radius you choose for your circle. The sine, cosine, and tangent functions will produce the same value regardless of what r is. And I just want to prove that to you. So in my picture right here, let's suppose that instead of this circle, right, which has a radius r, let's suppose that I had drawn a smaller circle, okay, like, say, this one right here. All right? And let's suppose that this smaller circle has radius r prime, okay, so some smaller radius. Now, if I had used this smaller circle, then I would be looking at this intersection point. Let's call this intersection point x prime comma y prime, okay? Now, if I use this definition for the trig functions, but use the smaller circle, then here's what comes out. I find that sine theta is equal to, okay, it's going to be the y-coordinate of the intersection point, but using the smaller circle. That would be y prime. Over the radius of the smaller circle, that would be r prime. Cosine theta would be the x-coordinate of the intersection point with, again, I'm using the smaller circle, that would be x prime. Over the radius of the circle I'm using, which is r prime. And then finally, tangent will be y prime over x prime. All right, so as you can see, I have two different definitions, or seemingly different definitions, depending upon which circle that I use. I claim that these expressions are actually equal, that y over r actually is y prime over r prime, and x over r is x prime over r prime. How do we know? The answer is basically similar triangles. Have a look back at your circle again right here. I'm going to draw two triangles, or actually I'm going to start by drawing two segments. I'm going to start from this point right here and drop a perpendicular line. So here's my perpendicular line, and it makes a right angle. As you can see, I've made one right triangle here. And then I'm going to do the same thing for my other intersection point. I'm going to drop another perpendicular line, okay, and it makes a right angle there. Now, as you can see, I've got two right triangles. And if you notice, they're actually similar. How do I know they're similar? Well, first of all, this triangle here, the smaller triangle, and the larger triangle, this one right here, they share this angle in common. So that's one angle they have in common. And then they also both have a right angle. You might remember from geometry that once two triangles have two angles in common, they're automatically similar. So the smaller triangle is similar to the larger triangle, which means that, if you recall from geometry, I have a whole bunch of proportionality statements. In other words, I can say that, this side divided by this side is equal to this side divided by that side. Remember all that kind of thing from geometry? If you look at the definitions of the trig functions here, they are, in fact, ratios of sides of these triangles. Because, have a look, this length right here, what is that length? It's the base of the larger triangle. But of course, this length is actually just the x-coordinate of this point, which is in fact x. So the length of this side of the triangle is x. How about this distance right here, the hypotenuse of the larger triangle? That's actually r, the radius of our larger circle. So that's r. All right. And then how about this shorter base right there? What is the length of that? Well, that's the x-coordinate of this intersection point, which is x prime. And then how about this hypotenuse right here, the hypotenuse of the smaller triangle? Well, that's the radius of my smaller circle, which is r prime. Now, if you remember your similarity statements, your proportionality statements from similar triangles, we can say that this side divided by this is going to be equal to this side divided by this. But that is exactly saying that this expression here is equal to this expression here. X over r equals x prime over r prime. We'll have a look. X over r is equal to x prime over r prime. So I told you that it doesn't actually matter what radius you choose for your circle in these definitions. And I've just proved it to you, because I've shown that if you choose two different circles with two different radii, the two seemingly different definitions that you get are actually the same because of similar triangles. Okay? Now, because it doesn't matter which radius you choose, and this is really important, because it doesn't matter which radius you choose for your circle, we will always choose a radius which is very convenient. we could all draw circles of radius 5, for example, to define these trig functions. Or we could all draw circles of radius 6. But the radius that is most convenient is the radius equal to 1. Basically because if r is equal to 1, then these fractions disappear, or at least the first two do. You have a 1 in your denominator, right? And the whole thing simplifies by quite a lot. So since r doesn't matter, or since our choice for r doesn't matter, we may as well choose a value of r that is convenient. We're going to choose r equal to 1. Okay? What that tells us then, if you choose r to be equal to 1, then these definitions actually become quite nice. The sine of theta is not y over r. Well, it is y over r. But if r is 1, then that's just y. And that's just the y coordinate of your intersection point. If r is 1, then cosine of theta is, yes, it's x over r. But if r is 1, then that's just x. In other words, the cosine of theta is just the x coordinate of your intersection point. Okay? Right. Okay, so before I move on and show you some examples of computing all of this stuff, I really want to convince you that this weird definition of the trig functions is actually in agreement with the old school right triangle definition. Okay? This picture here is pretty cluttered, so I'm going to make a new picture just to convince you that these old and new definitions are in fact the same. So here's the idea. Let's suppose we draw a circle. Could be of any radius you want, but let's suppose that r is equal to 1. Okay? So let's suppose that this circle is of radius 1. Or actually, it doesn't matter what radius it is. Let's just say it's radius r. Okay? And we construct our angle theta. Okay? Maybe it looks like this. Here's theta. We look at the intersection point right here. And we look at the coordinates of that point, x comma y. Now, let's have a look. The sine of theta is defined to be y over r. That's the y coordinate of this intersection point divided by the radius of the circle that we drew. I claim that agrees with the old definition of sine theta. How? Well, look, drop a perpendicular line from this point. We've got a right triangle. What is the length of that side of the triangle? Well, it's y. I mean, right, that's just the height of the point off the ground. And then what's the length of this? Well, that's a radius of the circle, so that's just r. Now, the old definition of sine theta said sine theta is opposite over hypotenuse. Okay, well, what's the opposite side of theta? It's y. And what's the hypotenuse of this triangle? Well, it's r. It's the same definition. Okay? So, and you can think about it similarly. You know, the cosine of theta is adjacent over r, but what's the adjacent side? It's x. So x over r. So the two definitions, the old definition and the new definition of the trig functions actually agree. Okay, so that's probably a lot of abstract stuff, and you're probably sort of trying to wrap your head around all of this. Let's do some examples, and you'll see that this is actually not that hard. Okay? So let's, I never defined unit circle, by the way, really important. The unit circle is just the circle of radius 1. Okay? Remember I said you can use any circle radius you want to find these trig functions, and we're going to use radius 1. Well, we call that circle the unit circle. So we basically use the unit circle to evaluate trig functions. Okay? All right, so let's do some examples. All right, let's find sine of 270 degrees. Not using the calculator, right? Remember, we started with this example. We started by looking at sine of 270 degrees, and the calculator said it was -1. That was really strange. Let's see if we can understand this with the new definition. So how does it work? So remember how you find sine of 270 from the new definition. You draw your angle in standard position. So we have one side going to the right like this, and then the terminal side opens counterclockwise until you reach the desired angle. Now 270 is basically 3/4 of a turn, which means the terminal side is going to go all the way 3/4 until it reaches down here. Okay? And now what you do is you draw a circle of radius r, but again, we're going to use radius 1. So draw a circle of radius 1. Okay? And we ask, what are the coordinates of that point? Okay? X comma y. What are the coordinates? Well, since this point lies on the y-axis, the x-coordinate is definitely 0. Well, what about the y-coordinate? Because this is a circle of radius 1, this distance right here is 1. I mean, that's a radius. But of course, because this point is below the x-axis, the y-coordinate is actually -1. Now, according to the new definition of sine 270, this is going to be equal to the y-coordinate of my point over the radius r of the circle that I chose. Well, the y-coordinate of my point is -1, and the radius of the circle that I chose is 1, so this just turns out to be -1. That explains why the sine of 270 is -1. Okay, how about the cosine of 270 while we're at it? Well, the definition says that's just the x-coordinate of this intersection point divided by r. Well, what's the x-coordinate of this point? It's 0. Over r is 1, so that's just going to be 0. So the cosine of 270 is actually 0. Quite interesting. Okay. Let's do a couple other examples. How about the sine of pi? Now, I hope it's clear that when I write pi here, this angle is in radians. If you see an angle with a pi involved, that means it's definitely measured in radians. So how do we do this? Well, you start by asking yourself, what does pi look like, the angle, in standard position? If you remember, 2 pi is a full revolution, a full rotation in radians, which means that pi is half a rotation. So you put your initial side along the positive x-axis, and then you do half a rotation. And that's what the angle pi looks like. Okay? So there's the terminal side of my angle. And now I draw a circle of radius 1. Here it is. And I look at this intersection point, the point where the terminal side of my angle intersects the circle that I drew. I need to know the x and y coordinates of this point. Well, it's on the x-axis, so obviously the y-coordinate is 0. Now, what's the x-coordinate? Well, remember, this circle is of radius 1. So this distance is 1, but of course it's to the left of the y-axis, which means the x-coordinate is -1. All right, well, so what's the sine of pi? Well, by definition, it's y over r. But, I mean, as always, we're choosing r to be 1, which means that this is really just y, right? We don't really need the r. And what is y? It's the y-coordinate of this point. Well, that's 0. So sine of pi is apparently 0. How about the cosine of pi? Well, that would be x over r, but again, since r is 1, that's really just x. And what is x? It's the x-coordinate of this intersection point. Oops, my lights just went off. I wasn't moving enough. Go back on, there we go. So what is x? It's the x-coordinate of this intersection point, which is -1. Okay? Cool. So, we can use the unit circle to evaluate trig functions in the manner that I just displayed. So let's do another example. So here's the thing. Here's a question. Is the sine of 299 degrees positive or negative? Without using your calculator, try to answer this question. Notice I'm not asking you to evaluate sine of 299 exactly. So how do we do this? Well, just draw the angle 299. Where exactly does that sit? Well, 270 degrees would point you straight down, wouldn't it? And 360 would be back where you started. So 299 has to be somewhere down there. I don't know exactly where it is, but it's somewhere down there. Now, so that's 299. Now, we draw a circle of radius 1. Here it is, right? and we look at the coordinates of that intersection point. Now, I got to be honest with you, I have no idea what those coordinates are, right? In the previous example, the point was like on the x and y axis, and it was kind of obviously, 0 or 1 or something. Here, it's not at all obvious what these x and y coordinates would be. But I'm not trying to find them. I'm just trying to ask, is the sine of 299 positive or negative? Well, the sine of 299 is just, it's y over r. This is a unit circle. R is 1, which means it's really just y. So the sine of 299 is just the y coordinate of this intersection point. I don't know what that y coordinate is, but it's definitely negative because it lies below the x-axis. So the answer is negative. Okay. Cool. Maybe just a couple more questions or a couple more examples. Here's my next example. Say theta is in quadrant 2, and the sine of theta is equal to 3/4. Find cosine of theta. Boy, that's kind of strange, isn't it? So look, let's draw a picture. Theta is some unknown angle. I don't know what it is. But I do know that it's in quadrant 2. That's this quadrant here. So whatever angle theta is, the terminal side is somewhere over here. Now, if I draw my circle here, what do we know? We know that the sine of theta is 3/4. And what is the definition of sine theta? Well, it's y over r, isn't it? So here's what we can do. If you look at this point right here and drop a perpendicular line like this, this point right here has some coordinates x comma y. And this y in the formula for sine theta refers to the y coordinate of this point. And r refers to the radius of this circle. It certainly seems like this side right here is y, and this side right here is r, the radius of the circle. Now look at what the information we've been given tells you. It says that 3/4 is equal to y over r. Apparently, y is 3 and r is 4. So apparently, this side of the triangle is 3, and this side of the triangle, that's the hypotenuse, is 4. Okay? Now, the question is, can we figure out the cosine of theta from this information? That's what we're being asked to find. Of course, cosine of theta is equal to x over r. X means the x-coordinate of this point. R means the radius of the circle. I actually already know what r is. It's 4. The only question is, what's x? Well, x is just the x-coordinate of this point, which we can figure out using the Pythagorean theorem. This side right here, what is that side? Well, it's sort of like the adjacent side, I suppose. So using the Pythagorean theorem, what we know is this thing squared plus this side squared, that's 9, right? 3 squared is 9, has to be equal to 4 squared, which is 16. So I find that the adjacent side squared is equal to 7. So the adjacent side is